use the product rule. First function prime multiplied by the second plus the first function multiplied by the second function prime and equals the right hand side prime, which is 0. Again, the variable in question is only this. I will move this to the other side and divide by x. So then dy over dt equals negative x, no, negative y over x dx over dt. I move y dx over dt to the other side and I divide by x. At this point I'm happy because I can plug in whatever I'm given. I am given that this distance is 4 meters, but I don't have anywhere to plug it in. But I will plug in x. If this is 4 meters, how much is x? Thank you. So when x is 8. I do have this. It was given to us as, I think was 1.6, yes. I do have this, now it's 8. And you can say, what about your y? Not a problem. I have, the relationship is right here. If x is 8, y must be 3. Because the product is 24. So if x is 8, y must be 8 times 3. Plug everything in. 3 times 1.6, my calculator, yes, right here. So 3 times 1.6, and now you can divide by 8. And this is 0.6, of course, with minus in front, absolutely. Negative 0.6, and I have to decide what is the measurement unit. So as he approaches, as the person approaches the wall, his shadow on the wall, at the instant he is 4 meters away from the wall, is changing at a rate of, decreasing at a rate of 0.6. What over what? Since it's a rate of change. And this is in meters. What is the measurement unit? Thank you very much. Okay. Let's move on to another type. And I'm sure many of you are interested in electricity. So there is a problem with two resistors. And I think I'm on page 10. Am I on page 10? Yes, I'm on 10. Okay, so we have this relationship. If two resistors with resistances R1 and R2 are connected in parallel, as in the figure, there is a figure, and this is how they are connected in parallel. I'm sure you remember. So this is R1 and this is R2 connected in parallel. Then the total resistance R, total resistance, this is R1 and R2, and this is the total, measured in ohms, okay, is given by this. This is a lucky type of problem. Why? I don't have to come up with a relationship. That is already done for us. If R1 and R2 are increasing at rates of 0.3 ohms per second and 0.2 ohms per second respectively, and you're going to tell me what this means, then how fast, here's our question, how fast is R changing when and you know that this what I'm going to write it, but I'm not going to use it till the very end. R1 equals 80 ohms, and R2 100. So let's read the problem one more time. If two resistors with resistances R1 and R2 are connected in parallel, the total resistance R is measured, all of them are measured in ohms, is given by this relationship. We are lucky, we have the relationship already. If R1 and R2 are increasing at rates of 0.3 and 0.2 respectively, how fast is R increasing or decreasing? We'll see in a moment, of course, increasing, when such and such happens. So how do I start, and what is given to us, and what is the question? I'm sure that by now you see the pattern in these problems. Something is given, a rate of change is given, or two in this case, and we're asked to determine a third one.
Are we looking for the R over D2?
Absolutely, thank you very much. That is the question. Given that R1 equals 80 and R2 equals 100. Good. What are these?
Would it be dr1 over dt and then dr2 over dt?
Perfect. Great job. Good. I don't have a lot of headache. I just need to differentiate that implicitly. Will I differentiate that? Of course not. I will differentiate this. To make my life easier. And yes, in this case, we have three functions of time. And yes, we will differentiate implicitly. And let's see what we get. We bring down -1. We subtract 1 from the power times the inner function prime equals. We bring down -1. We subtract 1 from the power, and dr1 over dt times the inner function prime minus, bring down -1, subtract 1 from the power times dr2 over dt. Of course, I'm going to multiply everything by -1. They're all negative. And then this is what we are after. So dr over dt is r1 raised to -2 dr1 over dt plus r2 to -2 dr2 over dt over r to -2. Well, obviously I have everything except r. So this is 80, this is 0.3, this is 100, this is 0.2, I don't have this. So now I have no choice, I have to solve this equation for r. So 1 over r equals 1 over r1 plus 1 over r2. Find the least common denominator, which is r1, r2. Multiply the top by r2, multiply the top by r1. So r2 minus r, I'm sorry, of course it's plus. And now I will flip both sides, or cross multiply, but that's easier. r1, r2 over r1 plus r2. and this will be raised to the negative 2. So ready to calculate this, I hope. So dr over dt will be 80 to negative 2, 0.3 plus 100 to negative 2 times 0.2 over 80 times 100 over 80 plus 100. Ugly, but doable. Careful how you plug it in. We need parentheses in the calculator. We need parentheses around the numerator. The denominator, it's okay. But the numerator, careful. Left parenthesis, 80. Power. I always put parentheses around that negative power. Depending on the calculator you have, please be very careful. Multiply by 0.3. Plus 100 to the power negative 2. I close the parenthesis. Multiply by 0.2. Close the parenthesis. I'm here. Now I divide. In parentheses. 800 over 18. Close the parenthesis. Power, in parentheses, negative 2. Oops. Negative 2. Close. And press enter. dr over dt, 0.1321. Measurement unit. Anyone? Measurement unit?
Ohms per second.
Thank you very much. Ohms per second. Great job. Okay, on Monday we are going to review, of course. And if we have time today, we'll do more problems. But I would like to finish up with a little bit of 3.10. And then we'll go back and do other problems with related rates. There's a ton of different problems. That can be addressed with the idea of related rates. Any questions on this problem? Okay, last item of chapter 3. Back to 3.10. I know I've been torturing you with this for a long time. Bear with me. Here's f of x. Yes, our best friend, point P, of course. And the coordinates are a, f of a. And yes, you already know what I'm going to draw next. And you're going to say, of course, the tangent. And yes, of course, I'm going to ask you what is the slope of the tangent at P. You expected that, I'm sure. Can anyone give us the tangent? No, sorry. Can anyone give us the slope of the tangent at P? Anyone? I know you know. Okay, I forgot to say something very important. Anyone? I know you do know that. What is the slope of the tangent line at P? It's f prime of A. So now let's determine the equation of the tangent line at P. Y minus y1 equals the slope times x minus x1, where this is A, this is f of A, and of course this is f prime of A. So y minus f of A equals f prime of A times x minus A. And yes, I'm going to move f of A. Have we seen this before? Yes, just last time, when we approximated delta x by dx. There was f of x plus f prime of x times dx. It's a different form of the same thing. Okay. Now, this expression, what expression? F of A plus this, I'm going to write it again up here. So, there are two different things here. F of x can be approximated by f of A plus f prime of A times x minus A, and this is called the linear approximation, also called tangent line approximation, at A. What am I really telling you? I'm telling you that near A, if you use the line to estimate f of x, or you use the function to determine the value here, they're going to be very close. So a function can be approximated by a line at any point where it's differentiable. This line will approximate the function near this value. This line will approximate the function near this value. This line will approximate this function f of x near this value. Of course, it's different. You cannot use this line to approximate here. You can use this tangent to approximate near A. You can use this tangent to approximate near this value of x, and so on and so forth. So a function, wherever is differentiable, can be approximated by a function that is linear. So any differentiable function can be approximated by a line everywhere where it's differentiable. The exact same definition is L of x, but this time equals, and this is called the linearization. It's the same thing. So f of A plus f prime of A times x minus A, but when we put the equal symbol and we're asked to find the linearization, it's the same thing. Linearization of f at A. That's all it means. We can always approximate a function that is differentiable by a line. And let's look at a couple of applications of this. Find the linearization. So we are given f of x equals sine x and A equals pi over 6. We are asked to find L of x, the linearization of function f of x at A. No problem. All I have to write is f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. And this will be a line that will approximate sine near pi over 6 at pi over 6 and near pi over 6. Okay, so what I have to do is determine this, but I know that f prime of x is cosine x. So then the linearization will be f of pi over 6, I know it's 1/2, plus cosine of pi over 6, I know is the square root of 3 over 2, and then x minus pi over 6. I will distribute the square root of 3 over 2x minus pi the square root of 3 over 12 plus 1 over 2. I have to find the least common denominator, which is 12, and this needs a 6. So I'm going to reverse it. 6 minus pi the square root of 3. This is the line that approximates sine near A. Or I would say, since the linearization is at A, the approximation will be near A. Okay, some other problems that I didn't get the chance to look at last time, still from 3.10. Something like we are given y equals natural log the square root of 1 plus t squared. And here we are asked to find the differential. Find the differential of y. How do I determine the differential of y, and what does it mean?